Well, thank you so much for the introduction, Rich. And it's really good to be here. And for my talk, I want to tell you about some work we've done at OpenAI, where we used very simple tools of deep learning in order to do things which seemed impossible at the time. Before I start with the talk, I want to say a few words. So, like Rich mentioned, I started working with Jeff a long time ago when I was an undergrad. And it's been really, really wonderful working with Jeff. We worked together continuously for 12 years. And I'm really grateful that I had the opportunity to do so. So thank you. And now, I will dive into some of our results, where we simply used large deep neural networks on lots of data, which is basically the connectionist dream. If you have a big neural network, it can learn a continuous distributed representation of whatever the data you give it. You just need to give it the right data. So let's start. I'll tell you one thing about OpenAI, is that our goal is to make sure that computers which are smarter than humans, which are as smart as humans, benefit all of humanity. And right now we are focused on making technical progress. And I'll dive into telling you about our work on large-scale reinforcement learning, starting with one of our most exciting results last year with the OpenAI 5, our Dota bot that was able to beat the world champions in Dota, the human world champions in Dota, in a live match. And I'll show you what the cast had to say about this.
The ancient will fall, and that is GG game over. OpenAI taking game 2, taking the series 2-0. After this second game in particular, this is a fantastic example of something that, as a player of Dota 2, as a professional.
So the thing you need to take from this is that the caster was excited. And we've had our bot play not only the world champions, but other 3 top-tier teams, and we've beaten each one of them 2-0 in a best-of-3 match, and with the world champions get a live match. And so I'll tell you a little bit about Dota, because I imagine that not everyone here may play this game. What you need to know is that it's a real-time strategy game, where you have partially observable state. You have long games, which last for almost an hour, and you have a large continuous action space. And another thing that's important to know about this game is that that professionals dedicate their lives to be as good as possible at this game. You have people who spend 10,000, sometimes 20,000 hours of deliberate practice trying to play this game as well as possible. And the annual prize pool in this game is $35 million. So it is a real sizable, it is a real game. People make careers out of playing this game well. And we were able to beat the world champions. And the way we did it is through very large-scale reinforcement learning. We used 45,000 years of gameplay. We used an LSTM policy with 150 million parameters. And we didn't use any human training data at all. The policy learn to play by playing many games against itself, self-play. And we did do some reward shaping to encourage the policy to do things like resource accumulation earlier in the game. But that's the recipe. It's simple. And that's the story of deep learning in general. The core is simple. The tools don't care which problem to solve. It's a very powerful hammer. And it worked. And here's a nice plot which shows the strength of our bot as a function of time, where the x-axis is log number of flops used to train the bot, and the y-axis is true skill, which is something similar to the ELO rate in chess. And we train it, and it got better, and if you train it more, it will probably continue to get better. So that's one of the attractive things about having an agent play against a copy of itself. It is able to generate its own training data. One other thing that we've done was to open this bot to the public. So hundreds of, or maybe even thousands of teams of people who really love the game, who really love Dota, played many games against the bot, trying to find a way to exploit its strategy. And our win rate was 99.4%, but some teams were able to find a gap in the strategy and to repeatedly beat the bot. So it means that there is still room for improvement. And this is a photo of the OpenAI Dota team together with the world champion team. So the OpenAI Dota team are standing and the Dota world champion, the human players, are sitting. And that was a really fun project. One fun note is that after losing to our bot, the human world champions started to play, they changed their game style, and they were able to win other teams with greater frequency and greater margin because of the games they played against our bot. And a paper with all the details is coming soon. So I want to talk about one other project which was very fun to make. It is very similar in spirit to the Dota project in that there is an environment and there is deep reinforcement learning, and you have agents which are playing a game against other agents. And the hope is that as the agents get better, the environment gets more complicated. So we wanted to see if we can design an environment where interesting tool use could be formed, could be created. So let's see. We designed this little box environment where the agents play hide and seek. So you've got the agents, they play hide and seek. You've got the blue agents, which are the hiders, and the red agents, which are the seekers. And at the beginning of training, they were just kind of flailing around and not really doing much. And then as training progressed, the seekers learned to catch the hiders. So then as training progressed some more, the hiders learned to barricade themselves, and the seekers couldn't get there. So after some more training, the hiders learned to barricade themselves, but the seekers took the ramp and used the ramp in order to get to the hiders. So then the hiders learned to respond by grabbing the ramp to prevent the seekers from catching them. And so the cool thing here, so like the motivation here was more or less along the lines of, like, it's pretty hard to design very interesting simulated environments. But we know that as the agents get smarter, if they are part of the environment gets more interesting. This is why the human world is interesting. It's because of the other humans. There are the elements, there is the rain and the sun, but it's really the other humans which make human society what it is. And so this was part of the inspiration for this work. Can we have a small environment, we will try a little bit to see if reinforcement learning can generate interesting complexity and some kind of slightly intelligent behavior. We've tried many variants of this. One of them was without, so here you have all these walls, here you don't have the walls, and now the seekers will move all the objects away. So you see the lock to the ramp, so now the seekers won't be able to use the ramp, so now the seekers cannot catch the hiders. The hiders have built a little fort for themselves. And here I'll show you my favorite thing here. So you see in this image, you see the seeker has created a little fort, and the seeker has also put those little lock icons on the two little ramps. So the intention was, well, if there is a lock on these ramps, it means that the seeker cannot get me in my little fort. But look what the seeker does. Just pushes the cube, and now it managed to get on the cube. And this was basically totally unexpected. With the previous hide-and-seek behavior, we kind of thought, this is what we want, so let's try to design an environment where the natural evolution of learning will produce those strategies, which they did. But it also did this thing, and that was unexpected. So how do you make of it? Is this creative problem solving? It's definitely creative. So that's interesting, in my opinion. So I think there is something very intriguing about self-play, and it's possible that in the future we may create far more complex and interesting worlds with very smart agents running their own little society there. But I forgot to mention one important thing about the previous results, is that we needed something of the order of 500 million episodes. So it was pretty expensive to get those simple behaviors. So you can correctly observe that deep reinforcement learning seems to be data hungry. And that means that it's great for computer games, and it's great for other simulated environments, but it can't possibly be applicable to the real world. And that's a valid criticism. But here I want to tell you about another result of ours, which is Dactyl, our humanoid robot hand, which was able to solve the Rubik's Cube. And here it is, taking the final steps in the solution. Now, the thing that we did was to train it entirely in simulation, and we tried to solve, and we actually we worked quite hard to solve the sim to real problem. Now I want to explain to you the big picture thinking here. From what you've seen from the previous results, from our work on Dota and from the work on the Emergent tool use simulated environment, is that deep reinforcement learning is very powerful. And if you have a good simulator, you can do a lot. You can do pretty much whatever you want. So when it comes to robotics, we can get a simulated robot to do whatever we want in simulation using reinforcement learning. And so our thinking was, well, clearly we can do anything we want in simulation. If we can also solve the sim to real problem, and somehow transfer our knowledge from simulation onto the real world, then robots could operate in the real world. And so I want to explain, just spend a little bit of time telling you why this is not a very simple problem. The fundamental reason for that is that you can't measure the real world well. Like, even take this Rubik's Cube, you don't really know what are the frictions of the different faces, and you don't know its mass precisely, and you don't know how different parts of the robot fingers will interact with the cube. And you can't measure its position with absolute precision, so you can't predict exactly how the cube will fall. It's a dynamic object, so you need to respond on the fly. So if you try to do a basic, if you just train something in simulation, and you try to naively transfer it, it's going to work very poorly. So I want to tell you about one very simple idea, which was the basis for this work. And that's domain randomization. So in domain randomization, we give up on modeling the real world precisely. Instead of modeling the real world precisely, we say we will randomize all the things we don't know. We don't know the mass of the cube, we'll randomize the mass of the cube. We don't know the frictions of various parts of the system, we will randomize them. We don't know the size of the cube, we'll randomize it as well. What it means is that you train a neural network policy and you put it in one of these randomized simulations, but you don't tell it which one. So in order to solve all these randomized simulations, the policy needs to adapt. It needs to learn to adapt. And if it's really good at adapting to to new settings and simulation, maybe it will be able to adapt to the real world. And I'll show you how it did. I'll show you a fraction of a video of the robot hand completing solving a full Rubik's Cube. and it succeeded. And if you paid attention during the solution process, sometimes it looked like the cube was almost falling and the fingers were catching it right at the edge. So clearly, it reacts on the fly to the circumstances and solves the problem. And one other thing I want to highlight is the idea of automatic domain randomization. One of the challenges that you need to address when you do domain randomization is to set the ranges of the randomization. How far should you randomize each parameter? And so here we've come up with a method which gradually increases the ranges of the randomization in order to make sure that the problem remains hard. So as soon as the simulated policy gets good at solving a particular version of the problem, we increase the ranges of the randomization to make it harder. So here in this image, you see the size, the range of sizes of the cube as training went by, as was determined by automatic domain randomization. This technique has two benefits. One of them is that it's much easier to tune hyperparameters. There is now this whole range of hyperparameters you can forget about. But the second is that the results are much better. It works way better, it achieves far better robustness compared to our best manually tuned domain randomization. And once again, we use large-scale reinforcement learning. The important thing to know is that during training time, we needed 13,000 years of experience in simulation. But then the policy network and the value networks themselves are quite small. And in this case, I'll mention a technical detail, that the value network had access to the secret simulation state which the policy did not have access to. So for example, when you put a policy in a simulated world and you don't know what some of the frictions are, the value function is permitted to know what the frictions are. And that accelerates learning by a fair bit. And so, yeah, if you use the standard way in which cubes are scrambled in tournaments, we can solve 60% of these scrambles. And by solve 60% means that we go from beginning to end without dropping the cube at all. So you're talking about 5 minutes of continuous operations where you do a very large number of moves. Now, if you fully scramble the cube to the absolute max, we can solve it 20% of the time right now. And there's reason to believe as the hardware and the sensors get better, the success rate will increase substantially. One factoid that may be interesting is that this robot hand, the company that makes them, sells about 10 of them per year because it's not clear how to program them. Now, once they become more commonly used, they'll become more robust and their performance will increase. I also want to show you some of the robustness performance. Here we do something which it was definitely not trained on, and that is the rubber glove. We put the rubber glove on the robot hand, and it takes it a little bit longer, and it struggles a little bit, but eventually it succeeds. Okay, so that's a substantial perturbation. Of course, you can improve it even further by, for example, training on real data, which this system has not done at all. It's been trained entirely in simulation. But it goes to show that even if you train in simulation, and even if you need a very large amount of reinforcement learning training data, you can, in fact, build useful systems which learn quickly, that adapt very quickly to the situation, even if it's one that wasn't really trained in simulation. So that's really the lesson, the message here. That even though deep reinforcement learning needs a lot of data in training, the resulting system can end up having the ability to adapt really fast. And I also want to show you a historical photo, which is the evolution of our different Rubik's Cube. For a while, we used sensors which are called phase space, where you have little light emitters which were embedded into the cubes. And there are special cameras which record the positions, which infer the positions of these light-emitting diodes. And so our first 3 cubes were based on the face space, and then the final last cubes were based on a sensor which measures the orientations of the faces, but the overall state of the cube was measured with estimated division. And that's the photo of the OpenAI robotics team. So, yeah, it's been a long project, and it was very fun to see it progress. And now I want to finish by talking about large-scale generative models, and specifically I'll talk about GPT-2, which is a language model which is large. And it turns out that when you make a large language model, it can generate text extremely well, and it can solve lots of NLP problems extremely well. And at this point, models like this have been shown on the internet a fair bit, and many people have seen how they generate text well. And here I want to spend a little bit of time talking about the history of our work, how we got from our sentiment neuron to GPT-2. And 2 years ago, we trained a large LSTM to predict the next character in Amazon reviews, and we noticed that the hidden state of that LSTM was extremely good at predicting sentiment. Then the transformer came out, and we thought that surely the transformer should be better than the LSTM. So we did the same work with the transformer, and that led to GPT. And already that model was able to achieve a very big improvement over the previous state of the art at the time when the model was released. And it was still a relatively small model. And then we released GPT-2, and it's just a large language model trained on high variety data, which is web text. And when this model came out, it was able to achieve very sizable improvements on lots of different language modeling tasks and on tasks like the vinograd schema. And I want to explain to you how the vinograd schema works and how it's connected with language modeling. So here's an example. The trophy doesn't fit into the brown suitcase because it is too large. So in this case, you can tell that the word "it" refers to the trophy. If you have a question, but instead if you say the trophy doesn't fit into the brown suitcase because it is too small, you can conclude that it refers to the suitcase. And so the way you test it in a language model, you simply replace the word "it" with either trophy or suitcase and measure the log probability. And you can just do that with language models. And another fun thing you can do with large language models is you can ask them questions and see what kind of answers they give you. And sometimes it works quite well. So for example, you can ask it, so here we took a data set from a question answering task, and we sorted all the questions in the test set by the confidence that the model has assigned to them. And also, by the way, I said test set, but I misspoke. This is all zero shot. So you simply sort them by the confidence that the model assigns to them. So you ask it, who wrote the book, The Origin of Species? And the model generates Charles Darwin. Let's see a mistake. Let's find a mistake. When was the first Star Wars film released? 1997. Apparently that's correct. So what would be a mistake? Yeah, so at the very bottom of this page, who played John Connor in the original Terminator? Here it makes a mistake. It says Arnold Schwarzenegger. So you can see one of its weaknesses. But nonetheless, it is quite encouraging that as you make language models better, they stop focusing on syntax and start focusing on semantics, which makes sense. Once you finish focusing on the syntax, what else are you going to focus on? Semantics seems like a plausible thing to do. Here's another example of summarization. I won't read it to you, but the thing which you need to know is that the whole thing is zero shot. What does it mean? We gave the language model these two paragraphs in the context. Then we gave it following those two paragraphs, we gave it a prompt with the question answer pairs on the right side of the slide. So the reason you do that is to zero shot teach the model that you want to answer a question. So you have question, answer, question, answer, question, answer, question, answer. And then you ask it the questions, did it climb any mountains? And the model answers Everest. And I recommend checking out these examples because they're quite cool. And again, all of this is zero-shot. The model was not explicitly trained to solve this problem. This is an essentially emergent property of doing language modeling well. And then other cool examples of zero-shot learning is that if you wanted to do summarization, you give it a paragraph, then you append TLDR, and it will generate something which will be a decent summary. And we've also achieved zero-shot translation. So if you say, here's a French sentence, it's equal to an English sentence, here's a different French sentence, equal to a different English sentence, and you only have 10 of those maybe because they need to fit into the context size of the language model, you can achieve a surprising degree of zero-shot translation. It's still not quite there yet, it has a long way to go, but it's encouraging that the model understands the task. Okay, I will skip the cool sample. I will talk very briefly about the staged release. So, we did not release the big language model at once. We released it in stages. We first released the small one, and then we worked with a number of university labs, studied these models, and released large ones. And the way I see it is basically, machine learning is getting more powerful. I feel like right now we are at the cusp of the end of the adolescence of machine learning. And in the future, models will be quite more powerful and quite a bit easier to misuse than they are right now. And so it is desirable to have a precedent for a staged release. So I want to finish by giving you a small bonus where you take exactly the same model as GPT-2 and you replace the data set to MIDI. And here's what you get. And it keeps going on for a long time. So, to summarize, what I've shown you some of the results that we produced at OpenAI over the past year. And the reason I titled the talk The Power of Deep Learning is because of the simplicity of all these results. We've shown that if you simply scale up reinforcement learning, you can solve very hard problems which seemed quite unsolvable before we did them. And it turns out that large generative models are similarly more powerful than was previously believed. And so I think that we will see a lot more exciting progress in the future. And so that's all I have to say. Thank you very much for your attention.